Welcome in the subject of engineering materials and metallurgy. I am Professor A.P. Godke, Assistant Professor in Department of Mechanical Engineering of S&D, College of Engineering and Research Center, Yavla. So today we will discuss about the phase diagram and different cooling curves applicable for engineering materials and metallurgy. So the Gibbs phase rule is the important rule to describe the phases of the material. So we know there are three important phases of the any material or metals are exist. So first is a liquid phase, second is a solid phase, and third phase is a gaseous phase. So these are the three distinct phases exist for materials. Out of that, the gaseous phase is not applicable, but liquid phase and solid phase are only applicable for the metals. So the to satisfy that phase, one of the important rule is there. So that rule was discovered by the Gibbs scientist, called as a Gibbs phase rule. So the statement of the Gibbs phase rule is that the Gibbs phase rule states that under an equilibrium condition, the following relation must be satisfied. So this is the statement of Gibbs phase rule that the equation is given or the one condition is there. So P plus F is equal to C plus 2. This is the condition. This condition must be satisfied for each and every metal or phase exist in the material. So where what is mean by this P, what is mean by this F, what is mean by this C, and what is the role of this parameter 2 or value 2, that we are going to see now. So P is nothing but a number of phases existing in the system under consideration. So how many number of phases are exist in any system under consideration, that value is denoted by a letter P. For example, there is a two phase, that is nothing but so the P is nothing but number of phases existing in the system under consideration. So, for example, for a solid, if there are two phases, that is nothing but a solid phase and liquid phase, or for any material or metal, two phases are there. At a particular temperature condition, the phase change can be occurred. So, if it is at room temperature, then that phase of the metal is a solid phase. So, that is one phase under consideration. And second, whenever that material is heated beyond its melting point, then the phase of that particular material becomes liquid. So the number of phases existing in a system under consideration are solid and liquid. So two phases are there under consideration for that particular example. Next, F is denoted as a degree of freedom. That is under the number of variables such as temperature, pressure, or concentration or composition. That can be changed independently without changing the number of phases existing in the system. So F is nothing but a degree of freedom that we are going to calculate. So in a particular phase, which type of variable is existing? So either temperature is vary, or pressure is vary, or concentration or composition, that is nothing but percentage of alloying element is going to vary. So that parameter we have to define. So which parameter is vary, or which parameter is going to change independently without changing the number of phases existing in the system. That value is denoted by a letter F. Then C is the number of components or element present in the system and represents and 2 represents any two variable out of the above three, that is the temperature, pressure and concentration. So here C is nothing but a number of components in the system. So how many number of components or elements present in the system, that is denoted by C. Then 2 represent any two variables out of the three variables, that is nothing but we are considering always three variable of temperature, pressure and concentration for forming any material, and out of these three for phase rule we are considering the two variables, so that two variable represented by this letter 2. So this is a theoretical formula for the this phase rule. Now we will move for the next, that is the Gibbs phase rule for practical application. So the most of studies are done at constant pressure, that is 1 atmospheric pressure. That is nothing but pressure is remains constant 1 atmospheric pressure, and hence pressure is no more considered as a variable. So we are going to neglect the pressure variable while doing the calculation for this phase rule. So for such cases, Gibbs phase rule now becomes P plus F is equal to C plus 1. So out of that three variable, temperature, pressure and concentration, one variable is a constant, that is a pressure, and that we are going to neglect. So here, hence in the above rule, one represent any one of the variable of the remaining two variable, that is nothing but temperature and concentration. In earlier case, there was three variables, that is temperature, pressure, and concentration. So we had used the two here constant parameter. Now here in case there are only two variables are there, so we are considering here any one of the variable. So this is the statement of the Gibbs phase rule, final statement of the Gibbs phase rule. P plus F is equal to C plus 1. Now next point is the cooling curves. So after studying the Gibbs phase rule, we can apply the Gibbs phase rule for the cooling curve to see the nature of the solidification process. So the cooling curve is a graphical plot of the phases of the element on the temperature versus time. So the resulting phases during the solidification is different for various alloy composition. So the most commonly curves are, so the most commonly cooling curves are pure metal, cooling curve for pure metal, cooling curve for binary solid solution, that is alloys, then binary eutectic alloys, and of eutectic binary alloys. So these are the four important cooling curves. Cooling curves are there, which are mostly related with the materials or metals, and for which we can define the, or we can apply the Gibbs phase rule. Now we will see the cooling curve for each and every metal. So for pure metal, so you can see here the graph of temperature versus time. So on x-axis there will be time, and on y-axis there will be temperature in degrees Celsius. After that you can see the different region, that is region AB, then region BC and region CD. So this is the nothing but the temperature decreases from higher point to the lower point. So from point A, which is at higher temperature, and at point D, which is at the lower temperature side. So you can see whenever the temperature is going to reduce with respect to the time, the phase change occurs for the material. So that is called as a cooling curve. So here now we are applying the Gibbs phase rule for every region. Now consider the region 1 or region AB. So here you can observe the region AB. For that, we are using the formula, our standard Gibbs phase rule, P plus F is equal to C plus 1. P plus F is equal to C plus 1. So here L means liquid phase or liquid state in region EB. Then L plus S for the region BC, L plus S means liquid plus solid phase. And for CD region, it will be S. S means the only solid phase exists for the material at that particular temperature condition. Now our aim is to find out the degree of freedom, means which parameter is prominent or which parameter is considered for the phase change. So we are applying the P plus F is equal to C plus 1 rule. So the first is a P. So what is meant by P? P is nothing but the number of phases existing in the system under consideration. So for this curve, for this region AB, only one phase, that is a liquid phase exists. So only one phase is there, that is a liquid phase for the region A and B. So P is equal to 1. So here we can use the P is equal to 1. Then we have to calculate the F. Next is the C, that is nothing but a number of components in the system. C is nothing but number of components in the system. So here see number of components or elements in the system, that is nothing but a temperature, pressure and concentration. So the number of component here for this curve is only temperature. So the number of components C is equal to 1 and 1 remains as it is. So after solving this, you will get the degree of freedom F is equal to 1. So here in this region AB, there is a no variation in the concentration, but there is a variation in the temperature. Temperature decreases, but the phase change does not occur. So the phase change remains as a liquid state. So between A to B, from this cooling curve, what we learn? We learn that for this phase, only temperature is going to change. Okay. Next, we will go for the next region BC. Next region for BC. So here, liquid plus solid state is there. So P, number of uh, phases existing in the systems are, so this is liquid one phase and this is solid second phase. So here it is a mixture of liquid and solid, means there are two phases existing in the system. So here P is equal to 2, F we are going to calculate, then C. So here number of components of the systems are only concentration. Okay, so here F is equal to 0, means here there will be no change in the temperature, there will be no change in the concentration. Okay, so no temperature and pressure varies, so a degree of freedom F is equal to 0. Okay. So temperature remains constant, only phase change liquid to solid. The amount of liquid going to reduce and amount of solid going to increase in this region B to C. Now for region C to D, we can see here the number of phases again only one, only solid phase is there. So P is equal to 1. Then F we are going to calculate. C number of components are the temperature. So number of components are here, concentration, that is the composition, and temperature is going to change here. So here F is equal to 1, means only one parameter is going to change. So here no change in the concentration occurs, but change in the temperature occurs. So here complete solidification of the process is carried out. So in this way, from liquid state, the metal is going to convert into the solid states. So in this way, we can learn the cooling curve for the pure metals.